Okay, so we'll talk a little more about measurement techniques, get into some nastier stuff. A little on instrument accuracy and the performance limitations, measuring Q, vector network analyzers again, uh, and the S parameters, which is what you're actually using, and some IMD measurements. Two main characteristics are resolution and accuracy. Resolution is the minimum value that can be displayed or resolved. The accuracy is how close that is to its actual value. Even though you might have resolution down to, infinite, whatever, the accuracy may be way off. I mean, you could have 1 volt accuracy and have resolution down to, microvolts. Frequency counters, like I said, are usually around 1 part per million on the time base. So, you're looking at possibly plus or minus 150 hertz in your measurement. If you're doing FT8 or something like that on there, you're way out of. Which of the following factors most affect the accuracy of a frequency counter? The most common test instrument that basically everybody has at least one of is the volt ohm meter or digital multimeter. The digital have high input impedance, usually they're FET front ends on them, so they have a very high impedance. Whereas the old volt ohm meter is going to have a much lower impedance, and it's usually they'll have an ohms per volt rating when you're measuring resistance or measuring voltage, and you multiply that times the total volt scale, which will tell you the maximum resistance on that particular scale. What is the significance of voltmeter sensitivity expressed in ohms per volt? Directional power meters measure forward and reflected power. They show you how much power is being delivered to the load, at least how much power you think is being delivered to the load. It's how much is going into the feed line. How much gets to the antenna is not necessarily the same. You could use these to calculate SWR. And if you look at the difference between the forward and reflected power, then you know that difference is being dissipated somewhere. Hopefully all in the antenna, but usually a portion of it is going to be dissipated in the feed line itself or any connectors along the way.
Formula you have written there doesn't show a square root symbol, but I recall the previous formula you should have had square root of power over power. And I don't see that. Was that a different formula?
No. Well, I don't think so. But if you have your calculator there, see if that comes out 1.67. It's possible I forgot to insert it.
I think you calculated one. That, the answer there is correct for what you have written on the screen, but if you put square roots in there, you get, I think it's supposed to be over 3.
But 1.67 sounds about right for that amount of reflected power. But I'll check it.
That's why I was wondering. If the formula-
Yeah, it's 1.67 with the square roots.
With the square roots?
Oh, no, without the square roots.
Yeah, that's what I said.
Oh.
I was saying 1.67, but with square roots, I get 3.
Created it.
Because 1/4 after the square root of 1/4 is 1/2. So
Right.
1 plus 1/2 is 1.5 over 1 minus 1/2,
Which is
0.5. So 3 over 1.
Yeah.
1.5 over 0.5 is 3.
Yeah.
So it's supposed to be like 3. If it's got square roots in it.
You have to go to slide 16 and previous one, you can see square roots there. The previous one.
The previous.
What this boils down to is which one of your formulas are you lying to us about?
I don't know. I never used the formula. I look at what it says on the meter,
Yeah, that's what I did.
or I look at the Smith chart where it is on the SWR circle. Or you look at the ratio of the impedances. So how much power is being absorbed by the load when a directional power meter connected between the transmitter and terminating load reads 100 watts forward power and 25 watts reflected power? Yeah, that's pretty much straight math. I think I got that one right. The Q of a resonant circuit, and we've talked about this a few weeks back. One way to do it is to look at the bandwidth of the circuit, the 3 dB points. And the narrower that is, the higher the Q. So that's one of the ways to measure Q if you don't have some sort of meter, if you can determine the bandwidth of the resonant circuit. Which of the following can be used to measure the Q of a series tuned circuit? A vector network analyzer can be used to measure input impedance, output impedance, reflection coefficient, and a lot of other things. You have to calibrate them, which is one sort of pain. The Rig Expert can be calibrated, but usually you don't, once you do it, you don't have to keep doing it. Although it's calibrated at the connector on the Rig Expert. So if you have additional leads on there, if you don't recalibrate, then those can affect the reading, but not much. And I guess same is really true with the VNAs. You know, by default, you're calibrating it at the output terminals. Usually they want you to do the calibration procedure at the device under test, as close as you can get. And you do it with 3 short circuit, open circuit, and usually 50 ohm, because that's what you're normally going to be working with. Sometimes you can do the full calibration where you actually do isolation and pass through. So if you're going to be testing like a filter where you're going to be looking at input and output, you want to do the pass-through calibration, which would be an S21.
Wow.
It would be an S21
That's
scatter parameter. We're coming to that. And those 3 calibration points are the 3 points on the Smith chart. The center and the ends of the horizontal real axis. Which of the following can be measured with a vector network analyzer?
Yeah.
Bill, that's good, it's going.
I don't know if I double clicked or just lost this chart. Which of the following can be measured by a two-port vector network analyzer? What three test loads are used to calibrate an RF vector network analyzer?
It's gotta be right.
More words, got it right in.
Yeah, that's usually true.
Fails.
So DNA can measure what we call S parameters or scatter parameters. I have no idea where scatter comes from. And I never bothered to research it because I don't care. And they're used to describe the effects of a device. So if we look at something like an antenna, a feed line, basically all we care about is the input and reflected back. So we only use one port. And the way the S parameters work, since all the network analyzers have two ports, the S parameters are input, output. So an S11 means you're looking at the input signal on port 1, you're looking at, and you're using the output signal of port 1. If I was doing an S21, I'm going to be looking at input coming into port 2 and output on port 1. So in other words, I'm sending a signal through, say, the filter, two-port network, back into port 2. So I'm receiving it on 2. Now, you can also do a 1-2 and a 2-2, but those are very unusual.
One thing again, you just said.
Input, output, okay? 1, input on 1, output on 1.
How can you have the input and output on the same?
Signal.
Because I have a transmitter and a receiver connected to that port internal to the device.
Transmitting down the line and measuring what's coming back, the same line into the same port and I'm analyzing. Think about like seeing this.
That's what your rig expert does too. It sends out a signal, it looks at what's coming back on the same port. It's doing an S11.
Okay.
So the two main uses are an S11 and an S21. And the 21, you're measuring the response of a circuit by sending a signal through it and see how it changes from what you sent.
And apparently that's what you cannot do with the rig expert, because it's going.
You can't do a 2-1, correct? Unless you're fast. Like in college, the small quick student in the physics book, they always talked about having a small quick student that could measure these things that they talked about. I guess you didn't have that book.
Fast students.
You just had a different textbook. Okay, so does everybody understand 1-1 and 2-1? Okay. We call 2-1 forward gain or loss. Usually it's loss, but if it was an active device, it would be gain. There's kind of a block diagram of the internal circuit, and you can see for over here, we're doing a 1-1 over on port 1 because we have that port connected up to the device under test. So we're sending a signal and we're looking at what's coming back. If we're doing a 2-1, we're over here on port 2, and we sent the signal in from port 1 through it, and we're measuring it back on port 2. The bottom one is the other alternatives, which very seldom see used. all you're doing is going in the opposite direction. So if you had I guess you would do that if you had a device that wasn't bidirectional, where you get a different answer depending on which direction you went. So what do the subscripts of S parameters represent? Which S parameter is equivalent to forward gain? Which parameter represents the input port return loss or reflection coefficient equivalent to VSWR? Okay, IMD, intermodulation distortion measurements. Normally you do what's called a two-tone test, where you send two audio signals that are not harmonically related. Typically they use 700. I've also seen 750 and 1900 because they're not multiples of one another. It's like trying to use prime numbers, I guess. Although it's easier to use rounded ones. And the idea is if I send those two tones through the device, I should expect to see those same two tones on the output. If there's any nonlinearity, I'm going to get mixing products. So I'll not only see those two tones, I'll see sums and differences and harmonics of them. So what transmitter performance parameter does a two-tone test analyze? Alpha. What signals are used to conduct a two-tone test? Yeah, you can't use I and Q, which would be alpha. Which of the following methods measures intermodulation distortion in an SSB transmitter? Pretty much got to be alpha or Bravo. Bravo.
Wow.
Well, the A's in our office, it's too early.
Oh, all right.
Yeah.
And make sure you read them all,
Well, he's trying.
because we had an exam this Tuesday and the guy missed one question. And he wanted to know which one. We showed him the question. And he admitted that he didn't read all four answers, or he'd have got a perfect score.
Speaking to Mike, and there's two harmonics into it. You got 700 hertz audio signal.
Well, I understand how that works on, I'm trying to read the difference between alpha and beta.
It's the difference between using two RF signals or using two audio signals.
Oh, there.
You're thinking of that.
It's only a 1 letter difference, just makes all of it. I didn't
Yeah.
see the RF.
It's just one letter difference.
Tricky.
Now, I don't have to read all four. You have to read them carefully.
Well, there, you keep adding stuff.
That's time supposed to be easy.
Yeah, that's right. Or else anybody could do it if it was easy. Okay, so we talked about time-based accuracy for frequency counters, input impedance on voltmeters, forward and reflected power for watt meters, bandwidth of a resonant circuit to determine the Q, VNAs doing an input-output impedance reflection and pass-throughs with the two-port and calibration with the three sources. S parameters is simply input, output. And a two-tone IMD measurement.